We've talked a lot about how a machine can understand text, but what about writing it? How does a machine generate a coherent sentence, one word at a time, when it literally can't see the future? It seems like a paradox.
Think about it. To choose the right word, you often need to know what the rest of the sentence is going to be. But the machine has to build that sentence sequentially. So how does it make a good choice at each step without knowing what comes next?
The solution is a really clever feedback system called an autoregressive loop. It starts with a simple start signal, predicts just one word, and then, here's the key part, it adds that new word to its own input and repeats the process. By the end of this explainer, you'll understand the engine that drives this loop, the transformer decoder block. So, at its heart, the decoder strategy is surprisingly simple. You can think of it as a tale of two attentions. First, the decoder needs to look inward, at what it's already written. This first part is called masked self-attention. It's basically the decoder's internal monologue. It's asking itself, okay, given the words I've already put down, what would logically come next? This gives it context from its own ongoing creation.
Now, the word masked is crucial here. The mask acts like blinders. It means the decoder is not allowed to cheat by peeking ahead at the words it hasn't generated yet. When it's trying to predict the third word, it can only see the first two. This forces it to genuinely predict the future, not just copy it.
Okay, so looking inward is step one, but that's not enough. The decoder also needs to look outward, back at the original prompt or source text. This is where the second mechanism, cross-attention, comes in. Here, the decoder asks a different question. Based on what I'm writing now, what part of the original input is most relevant? And the data flow for this is pretty neat. The decoder forms a question, which we call the query vector. This query is then sent over to the encoder's output, which holds all the rich contextual information from the source text. The decoder compares its query to all the available keys from the encoder to find the best match. Once it finds it, it retrieves the useful information from the corresponding value vector. So the decoder asks, and the encoder provides the answer. All right, so we have our two attention mechanisms, one looking inward, the other outward. Let's put them together now and trace the data flow through a complete decoder block.
The pipeline is very logical. First, the data goes through masked self-attention, where the decoder figures out the context of what it's already written. Then, it uses that context to query the encoder in the cross-attention step. Finally, the information from both of those attention layers gets combined and passed to a feed-forward network for some deeper processing.
You can think of this feed-forward network as the thinking part of the block. It takes the rich, combined context from both attentions and digests it. It's here that the model can learn more abstract, complex patterns before it's ready to make a final decision. After all that, we have a dense vector full of numbers. But we need an actual word. So, the final stage uses a linear layer to project this vector onto the model's entire vocabulary. This gives a raw score to every single possible word. Then, a function called softmax cleans those scores up and turns them into nice, neat probabilities. And this is what the output looks like. For example, if the model has just produced the word lay, the softmax might give the word shin a 75% probability of being next. The model then picks the most likely option, adds it to the sequence, and the entire loop begins again for the next word. So that's the mechanics of a single decoder block. But how does this one small component power the massive generative models we use every day?
Well, the real power comes from stacking them. A model like GPT isn't just one of these blocks, it's dozens or even hundreds of them stacked one on top of the other. Each layer adds a new level of abstraction and reasoning, allowing the model to build up incredibly complex ideas before making a prediction.
And this leads to a key architectural choice for practitioners. Encoder-only models, like BERT, are masters of understanding context, which makes them perfect for analysis tasks. But decoder-only models, like GPT, are built specifically for generation. They are the engines of creation.
If you remember just one thing, let it be this. The whole complex process of a decoder boils down to it repeatedly asking two simple questions. What have I said so far? And what from the original source is relevant right now? So the key takeaway is this. The decoder's power comes from separating its attention into two distinct jobs. It looks backward at itself, and it looks across to the source. This elegant division of labor is what allows machines to write.